This is Jeff Linderman, an applications engineer for GoEngineer. Welcome to my webinar on SOLIDWORKS Plastics. Today I will be covering the features and capabilities of Plastics Standard, Plastics Professional, and Plastics Premium. SOLIDWORKS Plastics was developed to help users predict and avoid manufacturing defects during the earliest stages of part and mold design, eliminating costly mold rework, improving part quality, and decreasing time to market. Plastics Standard was designed particularly for part designers. It will answer the basic questions: will my part fill, where are the weld lines, and will there be air traps? It will help determine the best gate locations and optimize part designs for manufacturing. Plastics Professional is geared more for mold designers and mold makers. It goes deeper into the injection molding process, allowing users to simulate both filling and packing stages. SOLIDWORKS Plastics Premium is geared for the companies that need a complete injection molding process analysis. Next, I'll be going through a brief explanation of the analysis available in each of the packages. After completing almost any analysis, the first plot one might look at is the fill time plot, which displays the profile of the melted plastic as it flows through the mold cavity and basically shows you whether or not the part will fill completely. Also displayed in the scale on the left is the amount of time it takes to fill the cavity. Another feature of SOLIDWORKS Plastics is the ability to detect short shots. Short shots occur when a mold cavity will not completely fill with melted plastic, as seen here. And frequently, higher injection pressures, faster injection speeds, and higher melt temperatures will not solve this problem. That is why it is so important to identify these kinds of problems before the mold is manufactured, because when this is first discovered in the molding machine, it can be very time-consuming and expensive to fix. Two more capabilities of SOLIDWORKS Plastics are the detection of weld lines and air traps. Weld lines are areas where two or more plastic melt flow fronts come together. This occurs when the flow front would have to go around a mold core feature and join together on the opposite side. They can also be caused by varying wall thickness that result in multiple flow fronts that flow through a mold cavity and rejoin at some point. And at any time you have two or more injection locations in a single mold cavity, it will have at least one weld line due to the two flow fronts coming together. The indicators seen here are areas where air traps would occur. As an injection mold fills with melted plastic, the air in the cavities is displaced by the plastic. This air is typically vented to atmosphere through vents machined into the mold at the parting line or in some cases down ejector pins. When the air gets pushed to an area of the part where it cannot easily be vented, it is referred to as an air trap. Air traps usually cause molded part defects that range from unintended through holes to burn marks caused by the combustion of the trapped air. SOLIDWORKS Plastics can identify the conditions that would lead to sink marks. Sink marks occur in relatively thick wall sections that are not packed out well enough to compensate for the shrinkage that occurs as the molded part cools down. They are called sink marks because the surface of the part actually sinks in, resulting in visible depressions. Sink marks can be improved or eliminated by changing wall thickness, gate location, process parameters, or even the material. And because sink marks almost always result in cosmetic defects, it is important to be able to predict them using SOLIDWORKS Plastics. SOLIDWORKS Plastics will also let you analyze multiple gate locations. Multiple gates may be required to fill very large parts, but they can also be used to balance the pressure within a mold cavity to prevent core shift and unbalanced filling. Because injection molding is a high-volume manufacturing process, injection molds commonly have multiple cavities, for example, 2, 4, 8, 16, 32, or more. SOLIDWORKS Plastics Professional can be used to analyze runner layouts. If the cavities are for multiples of the same part, there is the option to run a symmetry analysis on using just one part. This saves on solve time, and the solver will account for the total number of cavities. Plastics Professional can be used to analyze and optimize multi-cavity mold layouts to ensure all cavities fill at the same time and same pressure. If the runner system is unbalanced, the parts will not fill at the same time, and the resulting pressures will be higher on one part or may lead to a short shot. The runner balance tool runs through iterations automatically, making adjustments until the part fills with equal time and pressure. Insert overmolding is a process where melted plastic is injected over or around some other part that is effectively an insert inside of the mold cavity. The insert may be plastic, metal, or some other material. In this two-shot molding example, the hard rigid screwdriver handle is overmolded on the shaft, and then a soft rubber material is injected over the handle for the grip. Valve gates can be mechanically activated to open and close at specific times, and depending on their placement in a mold cavity, they can be used to control the filling profile of the plastic melt as it flows through the cavity, the location of weld lines, and the packing phase of the process. Now with SOLIDWORKS Plastics Professional 2017, the valve gate timing process is automated, and the valve gate timing settings are output with the results. For fiber-filled materials containing glass fibers, carbon fibers, etc., this analysis will predict the resulting fiber orientation and mechanical properties of a molded part. The next two examples available in Plastics Professional are co-injection and gas assist. Co-injection molding is when two polymers are injected into a single mold, normally one inside the other, so that one material becomes the outer skin of the molded part, and the second material becomes the core of the molded part. Here we're looking at a cross-section so we can see the skin material fraction at the end of fill. This gives us an idea of how thick the skin might be and if any of the core material may come through to the surface, which would typically be undesirable. For the gas-assisted injection molding process, a controlled volume of melted plastic is injected into the mold. Then gas is introduced into the melt stream to complete the filling of the mold cavities. The gas penetrates the center of the melt stream, coring it out and resulting in hollow parts.
Another useful tool in Plastics Professional is the part mass plot. The part mass plot shows the part mass changes during the filling and packing processes. This helps you determine when the cavity is fully packed so you can shorten packing time to eliminate unnecessary additional packing of the sprue and runners. Another study available in Plastics Professional is reaction injection molding. This is the process by which two reagents are mixed together and injected into a heated mold to react and solidify. Materials used in this process are classified as thermoset plastics. Once cured, thermoset plastics can have impressive heat and chemical resistance. An important difference between thermoset and conventional thermoplastics is that thermoplastic materials are injected into a mold hot and then cooled while in the mold. With thermoset plastics, the process is reversed. Silicones and polyurethanes are common thermoset plastics. And with Plastics Premium, you get all of the features of Plastics Standard and Plastics Professional with the added benefits of advanced cooling analysis and warp studies. The cooling analysis will simulate the thermodynamic effects of cooling channels, baffles, bubblers, and the mold. Cooling occurs throughout all stages of the injection molding process from the fill stage through ejection. The rate of cooling has a significant effect on part dimensions and influences part defects. If uniform cooling is maintained, the residual stress within the part can be reduced, thereby minimizing the risk of warpage and cracking. The warpage analysis predicts the shrinkage and warp in a part. Shrinkage is inherent in the injection molding process and is a contributing factor for part warpage. However, warpage is more complicated. Parts warp because of the combination of in-mold residual stress and non-uniform shrinkage. Factors that contribute to warpage are variation of temperature as the part cools in the mold, variation of pressure of the melt in the mold, and variable rates of shrinkage depending on molecular and fiber orientation. Now I'll go into the software and show some of the functionality within the program. So we'll start looking at this part as if we were a part designer using Plastics Standard. So the first thing you do when you set up a part for a study is create your mesh. I've pre-meshed these models to save a little bit of time on this broadcast. I've chosen a solid mesh since there is varying thicknesses on this part, and I'm going to end up doing a full warpage study at a later time. Once you mesh a model, you have the options to come in and refine your mesh. So I've refined the areas where radiuses are on the parts and different areas with thinner walls. So once we've meshed our model, our next step is to choose a polymer. There are over 4,000 different polymers in the SOLIDWORKS Plastics database. For this part, I've chosen a PC-ABS blend. If we look at the polymer material properties, there are settings for the melt temperature, mold temperature, ejection temperature, glass transition temperature, and your viscosities and all from the materials. So what SOLIDWORKS Plastics does, if you're a part designer and you don't know fill settings, pack settings, warp settings, or anything like that, the data in your fill settings comes directly from the material database. So once you've selected your material, the system automatically sets the recommended conditions for that material. So once we've got our mesh set, our polymer selected, our next step is to select an injection location. On this part, I've selected 2 injection locations on the side of the part. You also have the options to automatically add a location where the system will actually determine the best area to put a gate. In some cases, this area is not very convenient because sometimes the best area that the system will pick may be a cosmetic area on your part. So you'll have to choose a different position if you prefer. So now that we've selected our injection locations, those are the only steps needed to run the first flow analysis. I've already run the flow analysis to help save time, so we'll go straight to the flow results. So when you run the flow results, during the analysis, it'll actually start updating as it's filling, so you can see issues with it right off the bat. And one of the things that pops up during the flow analysis is your results advisor. So once again, you're a part designer, you don't know much about the injection molding process. The results advisor will show you and tell you, like in this case, this part's a short shot. So it means that there's a problem with the mold design or with some of the settings within the mold. So we will research that and see why it's a short shot. But as we look through the system, it'll actually explain each of your results during your filling stage of the process. So let's go back and look at our fill time. We'll run the fill time analysis and we'll watch it flow through the part. As you can see in these bosses here, the material's actually not flowing into those. So we need to figure out what the problem is in those bosses. So I'll stop this result. Within SOLIDWORKS Plastics, there's a really nice tool called Nominal Wall Thickness. What this does, it goes through and calculates the average wall thickness of your part and gives you 2 options of a way to view it. You have an option to look at it by percentage. So these red areas are either plus or minus 30% of the average part thickness. Or we can look at them by value. So it actually calculates a nominal wall thickness and shows you areas that are lower than that. So these areas, if we look that weren't filling, they're a lot smaller. So let's go and look at that area. If we look at that, you can see it's a very thin wall area. So I'm being integrated into SOLIDWORKS, we can come up and actually duplicate the study. When you select duplicate study, what it does, it copies the study you just did on the part. You can give it a new name. In this case, I actually I named this one called Fixed Short Shot. And that changes the configuration. So you're able to come in within SOLIDWORKS, run your study, duplicate the study. It creates a new configuration, and just as in SOLIDWORKS, it's a completely different configuration. You can come in and make geometry changes to the part. So I've gone in on this part. We'll go and look at my saved view again and made this boss thicker, added material to it, so the material should flow in there better. So since we changed the geometry, we have to remesh the model so the mesh will compensate for the new geometry, which I've done. I left all the mesh settings the same as before. I left reselected my injection locations as before, and I ran a new study. So we'll look at the flow results of the new study, and we can look at the results. We'll run the study, and you can see the part filling all the way through the bosses. So that's one way SOLIDWORKS Plastics can help a part designer that's working on a plastic part to be injection molded. They have the ability to come in and analyze and look and see if the part will fill. We also have the option to look at where areas of weld lines will be. So as we can see, since we have two gates, our flow front comes together and creates a weld line here. And if we watch the fill at the other end of the part, as it comes through all of these little ribs, it's also creating weld lines there. So it identifies that as well. We can also select air traps, and it'll show you areas that should need venting within the mold, where areas would be where air traps would be. So now I'm going to jump over to a multiple of this part and the mating part and show you a little bit of what Plastics Professional will do. Within Plastics Professional, you can use multi-cavities. It's got a handy channel design tool where you can come in and design your cooling channels or runners. So in this case, I'm looking at my runners. And to set up your runner system, you can come in and tell it diameters of your sprue and the runner legs and your gates. All of this is based on sketches, so you can just create a sketch of a particular runner design and run your analysis and look and see how things flow. And with varying parts, one of the major problems with a tool builder is balancing the runner system. So in this case, we'll look at the flow results from this part with the unbalanced runner system. So we've got a full meshed model. We've got the runner system. Let's look at the flow results. So if I back off the fill time on this part, you can see this part where after I back off, it has less material. This part's still completely full. So let's back off. Now we can see at what point this part is completely full of material at this point. And this other part has all of this area that still needs to fill. So what will happen here, for it to fill the part out completely, the system is overpacking this part, which will add additional stress to the part, which may cause more warpage within the part. So SOLIDWORKS Plastics has a runner balancing tool in which it'll show you your thickness distribution on your runner. It will come in and run number of iterations based on the maximum and minimum diameter and maximum diameter of your gates that you put into the system. It'll run through all of these iterations until it comes up with a balanced solution. So I'm going to switch over to the configuration I created for the balanced runner. We have a meshed model. We'll go back over to the runner balancing and show the thickness distribution. And when I started this, all of these were equal, and now we can see there's different diameters for the runner legs. And if we look at our flow results, I'll back off our fill time. I'll just go one click. And we see this part has an area that's unfilled, and so does this part. One click back, and they're both full. So what this does is it equalizes the pressure between the two parts. So you'll have a more uniform shrinkage and warpage between the two parts, and a more consistent molding of the part. So it'll open up your process window. So that's a good way to use Plastics Professional and design your mold. So now I want to jump back over to the original single part. I've set up a cool study for cool and warp. So when you're going to run a warp study on a part, it's beneficial to run the cool study as well, because this actually accounts for all of the mold temperatures and the average temperature during the cycle. So when you come in and mesh your model, you have the options of setting up a runner and cooling system design and a virtual mold. So I did that in this case. I have a virtual mold and I have cooling channels. These cooling channels, once again, they're based off of sketches. You come in and tell it the cooling channel diameters, and then you actually come in, you select a different, whatever type of coolant you're using in your system. They have oil, so if you run hot oil for molds that have to be heated above a temperature that water could stand, on this one I'm going to utilize water. And you also have the option for your virtual mold to set what type of steel it is. So the system does account for the thermal conductivity and the specific heat for the tool. So it accounts for that during the cooling analysis. Once again, the fill settings and pack settings I've left as default. These, you have the options to come in and change your melt temperatures, your mold temperatures. You can come in and set in advanced. If you run a flow pack switch point of 95 to 98%, a lot of processors do, you have that option. You can come in and set your flow rate profile settings. So if you set a different flow rate profile on your molding machine, you have that option as well. And the same thing for your pack settings. You can come in and set a pressure profile for your pack. In this case, I've left these all default. Come in and set your warp settings. You set your ambient temperature, which is the temperature outside of the molding machine where the part is actually cooling. It's accounting for that as well. And for your cool settings, you've got your melt temperature, which comes from your material database or comes from whatever your melt temperature is in your fill settings. So once we've got all of these set, we're going to use the cool pipe boundary condition. There's different boundary conditions for the cool analysis. In this case, we can actually come in to each individual cooling leg and select a temperature for that cooling leg, select its flow rate, and select the direction of flow. So these are things where you can come in and change your process to actually balance your cooling within the mold. If you see there's areas or hot spots of the mold, you can change the cooling temperatures and flow rates through that. So since we've run a cool study, we'll come look at the cool results. And this will give us an opportunity to look ahead of time before the part has even been in the molding machine, before the mold has even been in the molding machine, and we can look at the mold temperature at the end of cooling or the cycle average mold temperature. There's a measure tool within plastics where you can select different areas. If we select different areas on the tool, it'll show us the difference in temperature in those areas. So say we want to look at the temperature on the A side and B side of the mold, and it'll show us that these two have about a 9-degree temperature difference. So you can come through and look for areas where there's hot spots in the tool. You can slide through your clipping planes and find areas that are hotter than others and actually measure those areas. This gives you the opportunity to adjust your cooling settings to try to balance your cool temperature. And all this data can be used at the molding machine at startup to give a good starting point. So now that we've run through and looked at the cool settings, we'll flip over and we'll look at some of the warps. So within the warp results, we have total stress displacement. We have the options of choosing direct or absolute value. So your direct value shows a plus or minus scale. Absolute value will actually show from 0 to the maximum amount of warpage within the system. If we look, we have the options of looking at warpage in only the X, only the Y, or only the Z. In this case, the X direction would show like a linear or transverse shrinkage of the molded plastic. Our Z direction would show us the linear shrinkage. If we look at our Y direction, this would show us more of the actual warpage of the part. You have the option to come in and change your deformation scale. So it'll actually show you a more deformed part visually so you can see where the actual warpage is. And once again, we'll change this back to 1. Once again, you can come in with your measure tool and measure different areas on the part. So if we select 2 positions on the part, it'll show you the difference in warpage between those areas. So it's a handy tool for measuring overall warpage in your part. Also part of the warp studies in Plastics Premium is the sink mark profile, in which it'll actually show you areas of sink mark and it'll actually show you a measurable area of the profile, so you can actually measure how deep the sink marks are in those areas. And that concludes my webinar on Plastics Standard, Plastics Professional, and Plastics Premium. I've gone through and showed many of the features available within these studies, and also shown some of the functionality within the software. Thank you for attending this webinar. This is Jeff Linderman, Applications Engineer for GoEngineer.